Hello, welcome back. And we are going to continue the discussion about the thermal comfort part. In the last session, we do stop at the thermal comfort model. Frankel, okay? This thermal comfort model by Frankel actually trying to predict the mean vote for the thermal comfort by a collective group of people. Okay, and so the description here is a thermal comfort model using the predictive mean vote, which is the calculated one. Okay, derived it from the steady state heat balance. Okay, the people stay in a space for something long time, at least 15 minutes. Of a human body with an empirical constant, which determined from the experimental chamber test, okay, to some selected subjects for the thermal sensation. And the model was developed based on that sense. And the calculation will give a so-called predicted percentage of the satisfied index. And this index, first it established based on the calculated number of the PMV. This predicted mean voting for the thermal comfort, good or not, okay, based on this number, was a quantitative prediction of the number of the thermally dissatisfied persons among a very large group of people. So that the PPD, this index, actually is a percentage of people will feel comfortable. All right, and in this connection, this model, also known as a name, PMV-PPD thermal comfort model. All right, we do have some other measures to express the thermal comfort feeling. Operative temperature, effective draft temperature, a lot. Okay, but in this lecture, I only show you the details of this model. The model developed by Professor Frankel and looks very complicated, a very long equation, talking about the PMV, the predicted mean vote. Okay, the voting, okay, for the thermal comfort with the result 0 is a neutral. Voting 0 is neutral. So that calculate if this is equal to 0 means a neutral feeling, thermal comfort. On the minus scale, PMV less than 1 means on the cold side. Okay, more higher than 0 on the positive side means on the hot side. So that based on the calculated number, we can predict based on the 6 parameters condition, okay, we can predict overall for a group of people, the average, which number will be the final voting. All right, this is so-called the thermal comfort equation. The equation in here looks already complicated or 4 lines, and each of these parameters also associated another few lines of the calculation. All right, therefore, when we apply this equation for the handy calculation, we will feel complicated. Okay, so that also something more. Therefore, we do have quite a number of the written program to present interactively to calculate for us. You can find a lot, okay, through the internet, okay, through the program for that. I show you here one example available by quite a research center, UC Berkeley, so-called a CBE, thermal comfort tool. Okay, which will show you an interactive manner, a calculator. Okay, you may play around after the lectures here, which will provide you an interactive tool. You can change the temperature. Move directly. Okay, I'll show you again. Okay, can change the temperature. Okay, say 25 degrees Celsius within a thermal comfort zone. A higher the velocity, the thermal comfort zone move. Okay, to move. And the different relative humidity to showing this particular point. Okay, the condition, different metabolic rates. Okay, different cooling volume. all right, which is interactive tool available. We do have a lot of this kind of tool available. Okay, the mean volts. The thermal comfort model gives a number, so-called mean volts. Okay, and this mean volts are decided into a 7-point scale. Okay, and this 7 points is so-called a differential scale. Differential scale, the people can choose one most representative to his or her thermal sensation at that moment. All right, and this mean volts, the experiments actually conducted people submerged into an environment and asked to respond using the differential scale and also the dichotomic scale to express directly the satisfaction or dissatisfaction. Just two choices. Have to choose one. So that together with those can develop, okay, the percentage of people corresponding to each of these vote number and to the percentage of the group of people they feel satisfaction, right? So that the description here is the thermal sensation volts was an aggregate to obtain the mean volts for each set of conditions, and then the mean volts indicate approximately the average comfort sensation or occupants in terms of percentage. If we relate these two parameters A and B together, presented into a graphical form, say for a particular mean vote level for a group of people, okay, the total number that the people, okay, 20-something% may feel dissatisfaction, not satisfied with such a condition, right? Corresponding number here, okay, and now the curves showing there can be represented mathematically. Here is a mathematical equation. As the curve presented here, not so complicated. Sometimes we will rely on the graphical solution. Also, we can rely on the handy calculation of this. Okay, and this parameter y-axis is a PPD. The description is that the PPD is a quantitative measure of the thermal comfort of a group of people, many people, as a particular thermal environment, and come up with the percentage. Okay, means that a particular percentage may feel dissatisfaction. Okay, if the equation applied for the single people, this percentage could be a probability, the chance can be interpreted in that way. Not exactly the same, but we could interpret it that way. For the thermal comfort, we do have a lot of field study, many, over the half a centuries in the past, if not a million, if not 10,000, also at least 10, not 100,000, also at least 10,000. Here are some lists. Here are some examples. Okay, from the reference, the study have the regional basis, a different country, different culture, different functions of rebuilding and activities, different modes of the air conditioning system, natural ventilation, air conditioning, different time, year-round or some seasons, okay, and quite a number of the test subjects involved into the field study particularly, okay, few thousand. Although for few thousand, this number is not large enough because for the thermal sensation volts, the 7th scale, actually for the in-use space, basically the space tend to the accepted, so that most of the response will be concentrated on the neutral. But for the very extreme condition, it's very little. Okay. Sometimes, okay, this number of sizes relative to the big sample size is insignificant. So there are this they find quite a number of disagreement between the thermal comfort model of anger conducted in the chamber test and on the site test. All right. Now, the slide shown here just to draw attention that the thermal comfort developed and the chamber study may not fully describe the field situation. They will have some fine adjustment. But anyway, in there, I think at the level 2 study, what we expected from the thermal comfort study is we should know the thermal comfort is the mind of feeling expressions by human body, a state of mind. And this state of mind can be described by 6 parameters as proposed by Sir Professor Wenger. Okay, 4 physical parameters, 2 related human bodies. And these 6 parameters can be measurable. All right, and from these 6 parameters, the quantity, we can calculate, okay, the average mean volts for the thermal comfort by a group of people. And with this mean volt, we can predict how much portion of this group of people may feel dissatisfaction. All right, now we know this is okay. All right, for the thermal comfort model, not too difficult. Okay, the next, try to see your collective view. Let me build up a multiple choice for you. Let's see how was the response. How good you could understand about the thermal comfort model, thermal comfort in this lecture. Okay, not too bad. Okay, because this is just a theoretical description on the lecture materials. After the tutorial question, it will be much better. Okay, thank you very much. Okay, next one. Next topic on the indoor air quality. Indoor air quality, this is a term to indicate the indoor air quality with indoor space. Especially, we are concerned about the health related and comfort related of the building occupants. However, the terms here is not clearly defined enough because we now have 2 top issues. One is the health and other is comfort. Okay, so that are sometimes quite confused to us, also to me. Okay, which indoor air quality we're talking about? Some people were concerned about the health. For the long-term health effect, short-term health effect. Okay, some may are talking about the comfortable feeling. Oh, the smell not good, smell heavy, something like that. Okay, so that indoor air quality actually is a vague term. Okay, that the people to use it daily. The broad disciplines of the indoor air quality covers gases and the compounds on air, particles, microbiomes, contaminants, a lot of different mixture. Okay, inside the air. So that indoor air quality actually is a very huge topic. Okay, we need to spend at least a few number of subjects to describe it fully. In this lecture, we just show you some very simple, basic backgrounds of the indoor air quality and control. Okay, I think we do select starting from the guidelines for the indoor air quality certification scheme, and this is a baseline control in the legislative manner. Okay, and this legislation started, I think, 30 years ago already. Somebody talking about some control in terms of the legislation and policy level about the indoor air quality requirements, and at that and the collective results come up with a table here to list down some baseline monitoring, baseline control, which are dictated as for a certain time, and this certain time is an 8-hour average, which means that people will continuously put into an environment that's an 8-hour submerged, subject to the level of the parameter here will feel will be determined as an excellent level or a good level. All right. At that moment, some not quite meaningful, say the air temperature. Okay, these are actually not the pollutants. Okay, let's get rid of the thermal comfort parameters. We look at the compounds and substance inside the air. Say the carbon monoxide level. Say the RSP, which is the dust level. Okay, PM10, the suspended particulates of size less than 10 micron. All right, and here is the amount of the baseline level, which means if a people inhalation with a number of this less than 20 over 8 hours, okay, this exposure level will be classified as excellent. If less than 180 for 8 hours, okay, this particular level is classified as good. Okay, why 8 hours? Because when this baseline requirements established, it most likely related to 8-hour office work. So that for public safety also, say 8-hour office work. So that at the level showing here is an 8 hours exposure level. Okay, in this certification scheme, which lists down 9 parameters. Okay, for the indoor air quality: carbon dioxide, carbon monoxide, RSP or PM10. Okay, nowadays we're talking more about the particulates of fine particles. PM2.5 means the total particulates text sizes below 2.5 micron total. Nitrogen dioxide, ozone, formaldehyde, VOC, and this VOC, volatile organic compounds, is a lot. Okay, 10,000 or over a lot of thousands, right? And because of complicated nature, which calculated in the total amount, everything added together, all the VOC added together, come up with a level of TVOC, the total. And with this total manner, because each kind of the VOC, they have the different effects. Significant, not significant. Therefore, the total amount, this number, only is an indicative manner, just like an index to indicate roughly how worse or how good of the condition. Okay, of the same amount, they may have a different composition, similar to the particulate PM10. Okay, we do not know what kind of the substance contained inside this group of the particles: carbon, heavy metal, or silicon. Okay, all this added together. All right. Therefore, PM10, this total manner subject to the indicative manner. The radon, which are emitted gases, are radioactive by the granite, most likely, which you'll find very high at the basement. Airborne bacteria, okay, some bacteria. Also, newly introduced, say, the fungi, the fungus, also. Okay, amongst those, actually, we need to put a lot of efforts to understand them and describe them. Therefore, at the entrance level of study, this level 2, architecture and buildings and built environment, we will select one of the parameters as a surrogate indicator. Okay, for us. For the studying the indoor air quality, we do mention that we could by means of health effect or comfortable. Okay, in here we stick to an approach is a surrogate indicator. Surrogate indicator means the CO2 actually will not create a particular physically related health effect or the comfort feeling. Okay, actually people are quite insensitive to the CO2 levels. Okay, however, this CO2 levels in the normal indoor environment actually is a good indicator because high CO2, low CO2 is representative of some situation. Say for high CO2 means a lot of people emit smell. They do a lot of activities. Will associate with, say, the high dust level, okay, many VOC emission, so that the CO2, although is not the direct parameters, okay, to cause the health effect and the human comfort, but it is a good indicator to indicate that some other related parameter may cause the concern of the thermal comfort. Cause the concern of the human comfort and the health concern. Okay, so that CO2 as a surrogate indicator is proposed here. All right. Okay, description. Various study demonstrated that the measurement and analysis of the indoor CO2 concentration could be useful for understanding the acceptability for the indoor air quality, air conditioned and mechanically ventilated spaces. Okay, as I mentioned there are some relationships study between the indoor CO2 concentration and the indoor air quality. Here I list some examples, say the health effects of elevated CO2 concentration. Okay, say not directly related. For the health effect, the CO2 concentration should be very high. We're talking about the atmosphere. We're talking about 400, 450 ppm parts per million ppm, which is unit volume. And talking about acute instant effect, we're talking about the CO2 have to be elevated up to say 30-something%. Okay, 30-something%, 1 per 100, not per million. Okay, so it's a huge range of the CO2 tolerable limits. For people actually not very sensitive to that, I will show you some numbers. Okay, the study also the impacts of the CO2 to occupants' perceptions of indoor environments. Okay. People are not very sensitive to that, but they still have some sense. If a very poor of the indoor environments, they can distinguish from a very excellent environment, but it is not quite good to distinguish the good environment and the normal environment. Okay. The relationship between the concentration of CO2 and other contaminants, okay, some would be associated normally in the indoor environment, say the CO2 in the indoor environment and the TVOC and the particulates. Sometimes they have a not very strong but weak relationship. These two levels still independent. The relationship between the CO2 and the outdoor air ventilation rate is highly dependent. Okay. The next question is that we do have a lot of parameters. Why CO2 is selected? Okay, because CO2 is a metabolically produced by human body, easy to measure. Relatively easy, relatively less expensive. Okay, and in the air, CO2 is quite stable and will not react with some other substance and surface. Okay, therefore, in principle, CO2 can be used to evaluate the ventilation rate closely. Okay, determine the proportion of outdoor air is used in order to determine the recirculation air for the air conditioning system. Could be used in that way. In order to address one of the common indoor IQ control strategies is dilution. Basically, how to control the indoor pollutants. We have the 3 different methods. Okay, one is dilution. Dilution means we add in the clean air so that the pollutants level can be reduced. This is so-called the dilution effect. Actually, the common control is by means of the dilution, so that our calculation will stick to that. Okay. Apart from dilution, we do have 2 other methods. One is emission control. Say if we use the material less emission of formaldehyde, for example, okay, so that we will have some material got a certificate, the inventory, that's the material is safe to emit less than certain amount of the pollutants, emission control. And other one is the removal. Okay, we try to remove the pollutants directly from the air. Just for example, we install a filtration process to remove the level of particulates. Okay, so we stick onto the dilution effects in this lecture. Here are some facts of a CO2 as a surrogate indicator, some backgrounds. The first paragraph dictated that we do have quite stable CO2 level in the atmosphere, so that we can base on this level to do our calculation easily. I will show you one example later. And the second and the third paragraphs, okay, actually indicated that we do have quite a lot of studies and control agents to specify a good ventilation rate based on the CO2 level. Okay, the calculate say the baseline level 100 ppm, 1000 ppm, 800 ppm, and corresponding to a ventilation rate per person, we can calculate quite accurate. Okay, and for the CO2 factor C's, so here we have mentioned already. We can make sure we can apply it closely related to dilution effects. Okay, CO2 concentration do not provide a comprehensive indicator, but it's less expensive, so that we use it quite frequently as the first level of screening. Okay, first level of screening, and they also can be indicative of the absorbability of space by means of body odor. Okay, this body odor, okay, is calculated by a number of people subject to a certain condition. In a European country, they developed it for a standard people, standard height and weight, and bathing level. Bath level, how many times per day? Okay, and put the people inside rooms and then to ask the people to respond about the body odor. This is the study related to the CO2. Okay, under some circumstances, CO2 can also be used to estimate the building air change rate and fresh air at the AHU. I will show you the calculation in the tutorial question. And there is one study conducted by the OSHA. The people, okay, 8 hours, subject to 8 hours exposure per day by an elevated CO2 level. That's legally permissible because they found that no significant health effects to that 5,000 ppm, so that we can know about the tolerable limit is quite high. However, in some indoor environments, this CO2 level may be related to some other pollutants, so that they recommend an exposure limit of 8 hours, 1,000 ppm in indoor environments. Okay, because the build-up of CO2 may relate to some other indoor air quality concerns. They have established a lot of expressions to determine the level of CO2 and the ventilation rate for various arrangement of the ventilation system. Here are the ventilation system, okay, and as ventilation system, VAV, constant air volume, okay, and then the difference outdoor airflow mixing ratio. They have already worked out the equation, okay, for different parts. In the sheet here, my intention is to show you the CO2 is widely applied to associates, okay, with the air conditioning ventilation calculations. Okay, we just know this point is all right. Yeah. We will not use this equation in the examination or test. Okay, this one is more interesting. Because the CO2 is closely related to the human inhalation. Okay, each of the occupant will emit certain amounts of the CO2. All right, so that based on this fact, we can calculate quite accurately to relate the expected CO2 level in the space for the well-mixed space and the ventilation rate of the outdoor air, because background CO2 of the outdoor air is quite stable, 350, 400 approximately. Okay, based on the numbers shown there and the ventilation rate for rooms and the number of people, okay, number of people per person, all right? If we provide this ventilation rate for the long run, the steady state, well-mixed environment, the expected indoor air CO2 level will be 500, just by the mass balance, all right? If we reduce the ventilation rate for 10 liters per second per person in average, now it will be around 800 ppm for long run, steady state, so that we can calculate quite accurately in that way, okay? And also there is another information on this table about the dissatisfaction, okay, which also the Fender's study, this time not the thermal comfort but the indoor air quality acceptance, okay, corresponding to the CO2 levels. Certain amounts of people under the test condition will express dissatisfaction about the body smell, okay, so that here is a percentage of dissatisfaction under the test condition of the CO2 levels, complaint about the body smell. All right, yeah, we do have this kind of study. High level CO2 concentration in human. The main cause of lung and chest are getting oxygen from the air is inhaled to the body stream, and at the same time to eliminate the carbon dioxide level from the body through the air is breathing out. So that for the very high CO2 concentration, we're talking about 30%, 30-something percent, the respiratory failure will be occurred. All right. The measurements of the CO2 level in the bloodstream is not so accurate, so that I do not present you some expressions. The definition of respiratory failure. Okay, I listen here. Just we can read it as additional information for you. Okay, CO2 and other perspectives apart from the described the ventilation and satisfaction aspects. CO2 is metabolically produced and therefore can be associated with the presence of the occupants. Okay, say install a CO2 level sensor here, I can know, okay, how many people are there. All right, if we know for the known ventilation rate. CO2 is a relatively easy and inexpensive, we have mentioned it, very stable, mentioned it, material, just again, so repeat the one. Indoor concentration depends on the outdoor level and produce rate of CO2 within a space, so that we can make use of it to calculate for the ventilation system. In the office, quite a lot of office there, the dictated behavior, activities, this production is primarily from the metabolism, so that we can do the predictions relatively accurately for that. Okay? In some cases, not the metabolism dominated, the use of the CO2 may be less significant. Here is an example of some cases for the open gas cooker. Okay, they may, apart from the CO2 consumption, okay, which will produce, say, the CO. Although by making here is a further significant contribution about the CO2, also with the CO, also with the particulates, also with together with the VOC as well. Okay? To determine the contribution of the CO2 generated in the space, the difference between the indoor concentration, outdoor concentration have to be measured. Okay, these two levels. So that we have only the one equation, the IQ procedure to calculate for the CO2. Suppose a contaminant is is emitted or released within the ventilated space by human body. Okay, the emission of contaminants start at the time 0. Okay, put in the human body inside there, and then we monitoring the CO2 level. The contaminants concentration in the outdoor air is variable. Okay, so that we list all the variable in the constant rate of removal rate, constant, remain unchanged, and then indoor concentration, outdoor concentration. Okay, indoor concentration at the time 0, and the indoor concentration at different time. Okay, because we put in somebody inside, and then the room volume, also the constant rate of the production of contaminant, which is the breathing rate. Okay, we can make use of the parameters to calculate the behavior. All right, and for the concentration, we come up with a unit of a ppm. ppm in here by the sense of the volume. Okay, so that in some textbook they will specify ppm V. Okay, means, okay, this calculation part per millions by means of volume. This will be different because subject to the mass of it. Okay, some will be determined by weights, ppm by mass or by weight. Okay, part per million of the units, fractional concentration. And the equation, okay, we jump a few slides and then go back. The equation here related in there. At the time 0, initial concentration, and then we put in the source inside the room, and then we look at the time, the CO2 will increase accordingly, following the curve described by the equation. Okay, after some time, becoming steady, which is steady state. The whole equation, because time equal to infinity, this part, the equation can be simplified into the steady state equation. Okay, for the equation wise, it's simpler. Okay, look at the parameters. Here is an example measured by the ASHE. Okay, journal. Here's the source, talking about the CO2 production of a human body based on the metabolic activities. As we mentioned, okay, to measure the amount of the CO2 by the oxygen consumption method, by the breathing air, to measure the CO2 levels. And it's related to the metabolism process inside the body. Okay, here the relationship quite linear, easy to be predicted. Physical activity, a METs, so units. 1 MET, approximately the seated quietly. CO2 production rate is 0.25 liter per minute. Okay, higher the metabolism, resulted higher the CO2 production. All right, per humans, so that we can calculate quite accurately in there in this sense. And for the contaminant release is by the human body, so that G can be determined to there. Okay, and outdoor concentration quite steady. Indoor concentration, which is the baseline monitoring level. For the time period, actually the unsteady state will result for the very long time for the steady state exposure level, say 8 hours. For the unsteady state, we're talking about a few minutes, 10 minutes or 30 minutes, something like that. All right, and then we will have the ventilation rate, which is for the balance. For a balanced room, actually we take the ventilation rate coming into the room and then mixed. Okay, and the next slide, we're talking about the process, the concentration history. Okay, for this, and can be expressed mathematically. All right, look at the equation for the steady state. For the steady state can be expressed into two forms. We can rewrite the steady state expressions of contaminants attenuation as follows, which to help us to calculate the ventilation rate. Okay, based on the amount of emission, how many people there, and the dictated activities, and the targets based on the concentration, exposure concentration level, based on the fact of the outdoor CO2 levels. We can calculate the corresponding ventilation rate for design. And this procedure, so-called the IAQ procedure. All right. Here is a simple illustration example. This illustrative example serves for us to get familiar with the equation. Okay, the equation there. Okay, we visit. Okay, we get an example. The example is a living room of 5 meter by 6 meter by 2.9 meter with 4 people. Okay, the airflow rate was 19 liter per second. Okay, based on that, we try to do some calculation. If there are no airborne contaminants of health concern, a comment on the indoor air quality if each occupant produce 5 cm cube per second. All right, simple to put in the numbers into there. CO2 generation by one person, 0.05 liter per second, which is 5 cm cube per second. I think in there, most confusing step to me is the units. Transform the units. Okay, cm cube, dm cube, liter per second, liter per minute. Okay, air change rate, which confused me a lot at the beginning. So in there, I think we may spend some time. Okay, you are advised to spend some time to get familiar with those of the units. Okay, for all occupants, 4 occupants, therefore 4 multiplied by 0.005 come up with 0.02 liter per second. Okay, and then the ventilation rate is 0.19. All right, so we rearrange the equation. We do have a G, we do have the Q, so that we do have the outdoor concentration, CO2 350 or whatever level. We can put into the equation, or just can it simple to put the term, see the differences between indoor and outdoor become the change of the CO2 level. Therefore, we found that for such a condition, the CO2 level will be higher than the atmosphere level by 1053 ppm. Okay, so that we can make use of the ventilation procedure to do some analysis. Okay, here the explanation. Delta C is amount by which the indoor concentration exceeds or higher than the outdoor concentration, which adds by the emission indoor. For acceptable IAQ, delta C should be less than certain levels, or we may refer to the baseline monitoring baseline levels for the exposure. You remember these levels, the instant level doesn't mean the exposure level. Exposure level means submerged into the condition continuously for certain time of day, which are total inhalation at the aggregate effects inside the human body. The indoor air quality would not be acceptable under this criteria. Okay, for very high criteria. Here, 1,000 more, therefore 1,400. Okay, approximately. NOx and ASHRAE standard is to provide sufficient outdoor air to adopt proportions, whereas 800 ppm, 700 ppm, which is the baseline monitoring control level. Okay, here the last slide. The last slide for the lecture to show by the measurements. I think the measurements I did around 20 years ago to survey the conditions of the Hong Kong office, that the baseline, the certification scheme still under the volunteer levels and not yet received the sufficient attention. Okay, there is also the energy is a less significant factors at that moment. Okay, the people know concerned about energy, but do not react sufficiently in terms of the adjustment of the operations of an air conditioning system and other mechanical systems. So that the survey we found that The distribution of CO2 level in various offices in Hong Kong, and basically they are quite good, but some are very high. Most of them are below 1000 ppm, which can be classified as a good level in terms of CO2 if 8 hours exposure time is concerned. Okay, quite a large number of portion, less than 800. So that correspondingly we pay for that. For higher the ventilation rate, lower the CO2 level, but more energy will be used for the cooling. Okay, that's really the fact. Okay, I think for the lecture, we just stop the lecture here, and then we take a break. After the break, we'll take a look about the tutorial questions. Okay, and the tutorial questions already uploaded to the blackboard. Maybe you can take a look first. We will start the tutorial session at 4:30. Okay. Thank you very much. Okay, so that I just enjoy your break. Hello, welcome back. Here's the last session of this lecture, built environments and architecture and building. Okay, I hope none of the problems is fixed about the presentation. Okay, here is the last section. Can you hear me? That's okay. Because I just experienced some problems. Experience some network problems, not so stable. Okay, seems all right. Okay, let's continue. I prepared 5 questions for you, and I will leave some time for you to questions. Okay, let's show you the tutorial questions here. Okay, the first one is related to the thermal comfort and indoor air. Okay, first one is thermal comfort. Now, here in the lecture notes, we have mentioned that thermal sensation voting can be made by individual. Okay. However, the thermal comfort sensation, the models presents a collective views of the thermal sensation. Okay, so that which we relies on the average thermal comfort sensation vote. Okay, how this average vote be determined, which is the question number 1. Okay, question number 1 is that a thermal sensation survey has been made in a classroom with students' books being recorded as shown in the table below. Okay, which we have the voting score having the thermal sensation description. Okay, related to the book score. Okay, and together with the number of books made by this group and this class, right? We are required to determine the students' mean vote and the predicted percentage of the PPD as well. Okay, therefore the first step, we are going to calculate the mean vote. The mean vote actually will be weighted by the number of votes. Therefore, my suggested solution is that the total votes number, we calculate the sum of the number of votes together. In this class, totally we have collected 65 votes, okay, by the students. And the total score, which is the weighted score there, and for the score 3, we got the 0 number, so 0 multiplied by 3, and add 1 number multiplied by 2 score, okay, and then 4 number multiplied by score 1, and then 16 number multiplied by the score 0, and then so on. 33 of a minus 1 score, and 10 of the minus 2 score, and only 1 of the minus 3 score. So then we add up everything together, we come up with 50. For the 50, the negative values indicated that's of the cosine collectively. And now we divide it by the number of votes, we come up with minus 0.77, which indicates and overall the average effect is in between the 0 and minus 1, which is between the net neutral and slightly cool. Okay, for this 7 differential scale thermal sensation description, basically we will consider the slightly warm, slightly cool still within the tolerable limits of comfortability, so that we may estimate that we may interpret that most of the people there within this range plus or minus 1, and some may plus or minus 0.5, depending on what criteria we take them. Plus or minus 1, we will consider they are within the thermal comfort condition. Okay, and even under this thermal comfort acceptable conditions, some may still to make a complaint about the thermal incomfortability, not comfortable. Okay. All right. Therefore, the second part, we are going to determine the percentage, predicted percentage of dissatisfaction using the Fenger's model. In this example, we make use of the graphical methods. We do have a graph, something like that. Instead of the we also can make use of the equation. All right, just a direct substitute minus 0.77 to the PMV of the equation. Okay, and we'll come up with the number, which is the percentage of the PPD calculated. Should be the same. And in this given suggested solution, we just plot the minus 0.77 onto the x-axis and find the corresponding dissatisfaction is around 20%, 18%. Right? Okay, for this question, simple. Okay, seems straightforward, but most no response. Okay, not sure they are here. Okay, now the second question. The second question is also related to the thermal comfort zones. Okay, we just recall the graphs is over there. Here we have some examples of thermal comfort charts. Examples. Yeah, just four. We pick one of them as for this example. In this example, the thermal comfort measurements were made in an air-conditioned office. The daily measurements. Usually, this kind of measurements will be made when the FMO, Facility Management Office, receives some thermal comfort complaint. Okay, they will send some people to reassess the thermal comfort condition for the place or for the office, and then we adjust the set point of the air conditioners. Okay, to fine tune the condition, see whether they can solve the problems or not. Sometimes the complaint is made that is due to some other reasons. Actually, not much change, and then finally settle the complaints, something like that. Because the thermal comforts, once again, not only the physical determinants, but also we're talking about the state of mind, okay, the sensation of the feeling, right? Okay, now the question is that thermal comfort measurements were made in an air conditioning office. The air temperature and the mean radiant temperature are the same, were both 23.5 degrees Celsius. Okay, and provided with the chart below, we are required to determine the air speed required for comfortable conditions when the relative humidity of 40% and 80% respectively. Okay, the calculation. Okay, and C required to explain with the chart, okay, the different airspeed requirements in the part A and part B, correspondingly in order to produce thermal comfort effect. All right. Okay, we can assume the occupants had the Kelvin volumes of 1 Kelvin volumes and also the 1 metabolic rate. Okay, so that for the conditions on here, we need to pick the chart, corresponding chart, showing the 1 Kelvs and 1 met activity level. So the chart showing at the left-hand side corner. Okay, top left-hand side corner. Okay, and in our lecture notes, we do present you some charts and showing the condition there. So, for example, this one's steady 1 met and also 0.5 Kelvin values, and this one is 1 and a 1, same as the one we choose for the tutorial, and a 2 met, 0.5 Kelvin value, 2 met, 1.0 Kelvin values. We do have some others, so please get the chart required in the corresponding handbook. Okay, now for that, 23.5, there the x-axis having the air temperature equal to the mean radiant temperature. Okay, the condition. Okay, so that we plot a 23.5 over there. All right, and then we draw a line, a vertical line, and corresponding to the humidity, relative humidity, 40%, 83%, 40% line, this one, and 80% line here. So the corresponding 2 points in order to achieve the thermal comfort. All right, we need to maintain a certain air speed here for the thermal comfort for the 40%. Question A, the corresponding air speed is okay, I bring it reverse. This will be 0.15. Sorry, this will be B. This will be A. 0.15. This 9.1. Okay, this is a 0.2. So that in there is a 0.15. All right, and then for 80% is over there. Here is 0.2. This line 0.5. So that the air velocity is 0.35. Which means we need to maintain a higher velocity for the more humid air in order to have the thermal comforts predicted. All right, and then these are the use of the chart. And then to explain the different airspeed requirements, part A and B. Okay, we described it here, and to add some explanation for the 40% RH, which means it's a quite dry air. Okay, body could lose heat by evaporation effects. Evaporation effects can be described as a perspiration. Okay, perspiration and the vapor diffusion through the skin surface pores. All right, and therefore, for the RH increase, more humid air, this part, the heat loss by the evaporation, will be reduced. Okay, so that in order to maintain the same heat balance, same cooling values, and also the metabolism, we have to increase some other means of the heat loss. Okay, in this thermal comfort, the parameters dominating is the airspeed. Higher airspeed can promote, okay, the evaporation well. All right, so that the heat loss, increase the relative humidity, heat loss of the evaporation reduced as compared to RH of 40%. Okay, which means the heat loss from the other means shall be used in order to increase for the compensation of the heat balance. Okay, that's the example shown here. We are going to increase the airspeed so that the surface thermal resistance reduced. Okay, with the turbulence condition. Okay, so that we're promoting the convective heat loss. Okay, and this promoted can be represented by heat transfer, convective heat transfer coefficient. All right, finally reflected there. So that are the graphs here. To get the numeric results is not difficult, but we need to understand the mechanism behind about the thermal comfort so that we can give a satisfactory explanation about the calculations. See. Seems most of you taking rest. Okay, doesn't matter. You may refer. We may you may refer to the recordings. Okay, and then we study it. All right. Okay. Doesn't matter. Okay, and then the question number 3. Question number 3 here, the thermal comfort measurements were made in an office. Okay, same condition. And the air velocity is 3, and the relative humidity 50% is given. Now this time the air temperature and the group temperature is different. Radiant temperature, we do not have the values of the mean radiant temperature, but we assess the mean radiant temperature by means of the group thermometer, so that we come up with the readings of the group temperature, 23.5, which indicated that actually the body peaked additional heat gain by means of radiation. All right. We may assume that the group thermometer was a gray sphere of which the gray surface having an emissivity of a 0.85, okay, and then the diameter of 38 mm. Okay. All right. We receive a question about question 2 about the graphs. Okay. We leave it there first, and then we go back to the question 3 and how to calculate. For the graphs there, for the question 2. Now, how to read the graphs? The graph indicating the thermal comfort conditions to be maintained, okay, by means of all the 4 parameters. We have 4 parameters, right? Physical parameters, and plus 2 occupants related parameters. The 2 parameters already shown onto the graphs, so that the first job is to pick the correct graphs representing the human related parameters in terms of metabolic rate and the Kelvin volumes. Okay, and this is a 1 metabolic rate, 1 Kelvin volumes. The question is 1 Kelvin volumes, 1 metabolic rate, so that the graph is correct. Okay, first one. And then the remaining 4 physical parameters we have to get to there in order to achieve the thermal comfort. So the condition is that we do have the air temperature and mean meridian temperature specified here, 23.5. And the x-axis there is the air temperature and equal to the mean meridian temperature. So that the graph, firstly, we plot a point over here. Okay, 23.5. Okay, and then we draw a line, the red line. Okay, and then corresponding to the RH, relative humidity, which is the 4th parameter. Okay, we want the 3rd parameter, 1, 2 on the x-axis. The 3rd parameter is the RH. We plot the RH correspondingly, okay, onto the red line. Okay, and then what we are going to read is the 4th parameter. The 4th parameter is the velocity, relative velocity of the line of the inclined on the inclined line there of negative slope. All right, and we have 4 lines. Okay, the first one subject to the air velocity less than 0.1 meter per second. This one. The second line here for the air velocity of 0.2 meter per second. The third one is 0.5 as indicated there, and the last one is 1.5 meter per second, which indicated that in order to maintain the thermal comfort, we have to maintain the corresponding airspeed. All right. Correspondingly, in there for the 2 conditions, 40%, 80%, the airspeed have to be maintained in between 0.15 and 0.35. Okay, these 2 are getting reversed. Sorry, the first one should be a B, the second one should be A condition. Yes, and it's A, correct? So that for our judgment, we need to judge is the environment feasible to be maintained at such an air movement level. All right, if we within a reasonable region, say from 0.1 to 0.5 is quite reasonable. Higher than 0.5, we need an additional fan. So that in there, we can have some rough idea if the thermal comfort could be maintained. Okay, this is for the one. And other measures, in order to have the thermal comfort, we can adjust our cooling volume. And the entire graph here is for the cooling volume of 1. Okay, and this cooling volume of 1 is over there. If we reduced the amount of cooling, the whole zone will be shifted from there to the left-hand side, to shift it to another side. All right, so that we can adjust, okay, the thermal comfort condition as well by adjusting the cooling volume also. All right, is this all right to you? Yes, especially how to determine 40%. It's a 0.15. That's all right. Sorry for the typos. All right, seems we problem addressed here. Okay, let's continue for the question number 3. The thermal condition there. Okay, so then this question requires us to apply the mean radiant temperature equation. Okay, looks very complicated equations there. Okay, we are going to use the charts given below. All right, for the optimal operative temperature, determine whether the occupants would be comfortable, and this comfortable is divided with the predicted mean volve plus or minus 0.5. Okay, not plus or minus 1. If they had an activity level 1.1 met and a cooling volume cooling index of 0.5 cools the level, if not, suggest a solution that would make the occupants more comfortable. All right. So the calculation, the first step, we are going to calculate the mean radiant temperature because it's not given, but only the group temperature indicated. So that have to go through the complicated equation. First, we list all the parameters: cooling index, RH 50, group temperature by measurement 23.5 at the air velocity of 0.3 meter per second, air temperature 23, group diameter information about the group. Okay, so that we calculate the mean radiant temperature here. I list the equations, so sorry for the legends, a little bit inconsistent, but corresponding to the terms showing in the lecture notes there. Okay, the equation here exactly the same. Okay, and then we substitute the numbers 23.5 here. Okay, and then which is a K value, Kelvin scale, and then we put in the velocity, okay, emissivity, diameter of the group, okay, and then the temperature, group temperature, and the air temperature. Okay, finally the calculation to show the mean radiant temperature a little bit higher, which is 24.6. Okay, for the physical phenomena, because there's some air velocity surrounding the group, so that there's some heat lost. Therefore, in there also the group color is not perfectly black, not the black body perfectly. Okay, and so that is not so effective to perceive those of the thermal radiation heat flux. Okay, so that by the estimation, the heat flux, the average, okay, radiant temperature should be 24.6 in average over the surrounding. Okay, a little bit higher. So for that, we put the operative temperature onto the graph, which is calculated by the equation there. The equation here, okay, which is the operative temperature, which is the weighted sum between the air temperature and the radiant temperature. Okay, and for the velocity of 0.3, that's the level. The coefficient should be the 0.6. So that we put in the 0.6 over there, 0.6 over there, weighting which weights the air temperature and the mean radiant temperature. Come up with the operative temperature, which is a single parameter talking about the thermal comfort effects due to the overall, okay, temperature on the skin, which is 73.6 degrees Celsius. So that we put the x-axis, operative temperature, 23.6 by the red line over here. Okay, and then for the RH 50%, RH 50%, okay, correspondingly will be there. All right. For the shaded area, indicating the thermal comfort zone of the PMV plus and minus 0.5 limits, which is thermal comfort. Okay, and we found that the points fall within the one Kelvin level, okay, which is thermally comfortable. All right. However, in this question, the personal parameter is a 1.1 MET. Where's 1.1 MET? This graph is for the 1.1 MET. Okay, suppose the graph is for the 1.1 MET, but in there we do this thermal comfort point fall within the 1.0 Kelvin level, which is outside the thermal comfort zone of 0.5 Kelvin level. All right, so that for this question, the people, okay, the person will not be thermally comfortable. Okay, so that the second part of this question is that if not comfortable, suggest a solution that would make the occupants feel more comfortable. Okay, we look at the graphs there. We have a several way to have the thermal comforts. First, we can increase the operative temperature, right? Increase to the right hand side, so that the point move between the shaded area of 0.5 Kelvin envelope. Right? How to move the point to the right hand side? How to increase operative temperature? We can look at the equation. Okay, we can increase the air temperature. Okay, we can increase the radiant temperature, but the radiant temperature is relatively difficult. We can have a radiant heater. Okay, we could do that, or just an air heater to increase the air temperature. Okay, or we can reduce the air speed. Is this possible? Reduce the air speed. Now we will have is it not? Oh, it's okay. It's not so effective to change the airspeed in there, right? For this thermal comfort model, we also can increase the humidity. Therefore, the point will be moved upward. Okay, increase the humidity up to 60%, 60-something percent, and 60 to 65% is probably the point will fall within the envelope. All right, but the increase in humidity, which is quite difficult to control as well. Okay, and so that we can try to adjust the parameters to move a point, and so that this point can fall within the 0.5 Kelvin value envelope. This will become more comfortable. I think, or of course, we can put on more Kelvin. Okay, increase 0.5, become a 0.65, 0.75. Okay, things like that, or just 1.0. All right, according to the graphs. Okay, question 3. See whether you have questions about the question 3. Okay, seems a lot of you are keeping away. Okay, the last two. Question 4. An office measure of a particular size measured there, which is related to indoor air quality. And for the IAQ, we focus on the indoor IAQ procedure. Okay, so that corresponding to the lecture notes, the equation. Okay, and And the equation here is a transient state. But for most of the designs, ventilators design, we concentrate more on the steady state as an indicator, okay, surrogate indicator for the design condition. All right. Okay, we will make use of this equation and get familiar with it. Of these two, actually, is one example. So, here, an office, we have a measuring size, and this has a design occupant space allowance of 8.5 meters square per person. So that when we doing the layout, okay, approximately the area we will approximate how much of the maximum occupancy of the building, which is the facility coefficient. Right? And we are going to determine the design outdoor airflow rates correspondingly to the design occupant load in this room. Okay, and suppose we have a design designated ventilation rate of 8 liter per second per person. All right. So the firstly, we are going to determine the amount, how many people will be assigned into this room by the occupant load factor 8.5 meter square per person. So first of all, we are going to determine the area of office. Okay, in total it's 800 meters square. Because the equation here, we also have the ventilation volume there. Okay, so we are also required to determine the room volumes, which is 2200 meter cube. Okay, and then expected rents, the total floor area divided by the occupant load factor, okay, which is 8.5. Okay, so that finally we come up with around 94 persons in this room, which is a very big room. For the ventilation rate, 8 liters per second. Okay, ventilation rate 8 liters per second. There, ventilation. Therefore, multiplied by 94 persons, will come up with 752 liters per second. Okay. Then we transfer the units because we are going to determine the design outdoor flow rate in a units of a so-called air changes per hour. Air changes per hour is a particular parameter talking about, in average, how much room volume of air be replaced in an hour. One air change hour means, in average, entire room air will be replaced by one time within an hour. 2 ACH means the entire room volume of air will be replaced by twice an hour, okay, and so on. All right. So that in order to calculate the air change per hour, as compared to units of liter per second, we need to convert the units, okay, from the liter to meter cube, from second to the hour. All right. So that the transformation. Liter per second, okay, multiply the factor, come up with the meter cube per hour for the design ventilation rate, corresponding to 8 liters per second per person. Okay, so that the air changes rate, which is the number per hour, therefore is a ratio between the 2200 and 2700. All right, so that our calculation in here is a 1.2 ACH. Okay, 1.2 ACH is quite a typical numbers, okay, quite typical numbers for office. 1 ACH, 0.5, 1 point something. This air change rates replaced, we have to dictate the meaning for that. What air change, what air is to be replaced by what kind of air? In this question, this ventilation, we're talking about the outdoor air, which means fresh air, okay, to replace the already inside the room. Sometimes, and this replacement not goes to the fresh air, we need to specify. Now, which goes to the conditioned air, so that some people may use the air change rate, air change per hour, by air conditioned air, which is treated thermally, okay, cooled down. Okay, therefore these two numbers, okay, sometimes can be mixed if we do not explain it explicitly. Usually we do not explicitly mention most likely. 80%, 90%, most likely referring to the outdoor ventilation. All right. See whether you have questions for this problems or any points you want me to clarify for the question number 4. Okay, neutral. Okay, the last question. The last question is similar, but for this question, we are going to get familiar with the equation, particularly for the transient condition. Okay, so the question is like that. There is a room, has a volume of 60 meter cube. Okay, and the ventilation rate is 3 air changes per hour. Okay, and the total CO2 generated by all occupants is 3 liters per minute, which is given also. And now we have the generation rate. Okay, and the occupants will arrive at the room together, supposedly, just like a classroom. Okay, and the initial room CO2 concentration at the ambient level, which is outdoor, supposedly at the level of 350 ppm. Okay, so that we are calculated for 2 conditions. One condition is a transient state. Okay, once the people coming in at the time 0, at some time, what is the corresponding CO2 concentration? All right. The second is at the steady state, what is finally the CO2 concentration? All right. And for the steady state, we we also can determine what's the steady state time and compare to the occupation time. Is it significant to concern about the steady state, things like that. Okay, we list the input parameters. Volume 60 meter cube given, air change rate 3 per hour given. It's better to specify the unit, and generation rate of the CO2, which is the emission, which is 3 liters per minute by all occupants. Okay, and the CO2 outdoor levels is given 350. Okay, so that the equation, the listed equation there, and the outdoor ventilation rate correspondingly, which is the 3 air change, which we are required to ventilation rate. We have to, because the ratio is over there, we need to unify, make it into the same units. Okay. For the outdoor ventilation, we calculated the 3 air change come up with 0.05 meter cube per second. So that for the generation of CO2 emission rates have to be converted to the units of meter cube per second. Okay, so that for the conversion, liter divided by liter per minute. Okay, we have divided by the hour. Liter per minute, outdoor rate 3, liter per minute. Okay, liter per minute. Okay, it's there. And then the outdoor ventilation rate is there. All right, and then we substitute into the equation for the A for after 1 hour, and the CO2 levels is 1,300, and steady state we put in the equation is 1,350, which is very close. So that if for an office we're talking about 8 hour exposure time, this transient state are less significant. However, for the lecture, say 1 hour, okay, tutorial, this probably exposure level, okay, this transient state may be a concern. We can make use of a lower concentration rate so that we can save some energy because less amounts of the outdoor air cannot coming in. All right, there's some implications about the level to apply. The levels calculated by the equations here. Okay, so that's the remaining time. Thank you very much for this class, and the remaining times allows for you around 10 minutes to see whether you have the questions. I can try my best to refer your questions, to respond to your questions as well. There is a typo over there. Okay, there's a typo over there. Typo for the question 5. Question 5. Typos G equal to 3 divided by 60 times 1000. Okay, please correct it. Here is a typo. Okay, we have one question: how to find the values in the question 3. Which values? The values. For the question 3, okay, we have determined to give a number of values. For the mean radiant temperature, we make use of the equation. Okay. For the operative temperature, we make use of another equation. Okay. For the thermal comfort zones, we make use of the graphs by plotting the operative temperature calculated and the given relative humidity to fix a point. And then to see if the point fall within the envelopes of thermal comfort zones, which defined by the cooling volumes. Okay. If not, we try to see how to move the point correspondingly to the parameters so that the point finally can fall within the envelopes of the thermal comfort zone. Say, for the operative temperature in increment, okay, we can adjust by the equation, okay, to have the higher air temperature or higher radiant temperature or both. Okay, so that we are not going to find the values, but to understand how the mechanisms of the thermal comfort associated and presented with the equations here. All right. I hope this is informative for you. Any further questions? Just to review, okay, the content, and if you have any questions. Values of A is a constant. Yes, a value of A is a constant. in the lecture notes, the constant use the different legend. Okay, here using a constant of the COP, which is of the constants of A. Okay, and this constant is related to the air speed. Okay, for the air speed between the point 2 and 0.6, the constant will be 0.6. Okay, and for the low air speed, the constant will be 0.5. Okay, for higher the air speed, higher than 0.6, therefore the constant will be 0.7. So that yes, this is constant. Yes, it is a constant related to the air speed. And I find the constant on the lecture notes. On the PowerPoint page 5, as shown in there, I have highlighted on the screen here. The legend is different. COP actually is the values of A. Okay, seems this is not a very difficult topic. I think after the study, preparing the materials, every one of us can handle the topic well for the entrance level, for the thermal comfort and indoor air quality. The next time we will start another topic about acoustic. We will acquire the basic acoustical parameters and the measures for the noise control, acoustic, the basic units calculation, as well as the noise exposure as well, which will be the indoor environment standard basics. Okay, thank you very much for attending the lecture today, and see you next time. Thank you.